Hi, I am Andrea Mattioli, a research fellow at the HIS laboratory at East CNR and a PhD student at the University of Pisa. I will introduce this work done in collaboration with my advisor Fabio Paternò. Nowadays, connected objects and sensors are always more present in our daily environments. A way to capitalize on the possibility offered by this landscape is through trigger action programming. Trigger action programming is an end-user development approach that has proven to be usable even by people without programming experience. Basically, it concerns the creation of automations in the form when something happens to the environment, if these conditions are satisfied, then activate some actions. However, this apparently simple structure can present some difficulties. For instance, the selection of the correct object and functionalities can be challenging for non-technical users. A possible solution is to use AR during the automation composition process. AR can be useful to dynamically narrowing the selection process to the user, to facilitate the mapping between digital and real objects, and to make more perceivable the task-related concepts. Some approaches explore the use of AR in smart homes, for instance to superimpose information about the state of the devices over them, or to control one or more nearby objects. Fewer attention has been given to generating automations involving multiple objects placed in different spaces. Moreover, they often focused on dedicated devices such as HoloLens. The potentiality of AR using mobile phones is still not fully exploited. After analyzing the literature, we define a list of requirements for the solution. The first is to remove the need for a detection phase before interacting with the environment. This because going near to an object and wait for the recognition can be a nuisance and limit the benefits of AR. The second is to allow for more expressive rules, because many useful behaviors cannot be expressed using a single trigger, single action structure. The configuration process should continue seamlessly after a rule element has been configured. The third is to provide visualization that support user control and understanding of the environment's automations. For instance, it should be easy to perceive if an automation is present, can be defined, or it is currently in editing on an object. The fourth is to provide rule recommendations that match the possible user intents in the rule creation phase. This because it is expected that AR application also provides some assistance during the use, in this case the configuration process. The fifth is to allow the selection of external services to be assessed in relation to home objects, because it is expected that services such as weather and notification will be used as trigger and actions. The sixth is to combine 3D abstract representation and 2D mobile interfaces. In a domotic environment, the fidelity of the digital objects to the real one is not a strict requirement. Hence, to improve the scalability and also to limit possible occlusions deriving from many 3D objects in the scene, a mixed 3D-2D solution was adopted. The developed solution is an Android application implemented using Unity and the AR Foundation library. It allows users to create, modify automation, and also to explore the environment, visualizing which automation has been created. Its main features are that there are no need to go near to an object and wait for the recognition. User can move about and select the object to use or load external services from the menu. Different graphical elements are used to visualize some aspects of the automation composition process. Some textual description about the created automation are placed over the objects they refer to, and also recommendations are dynamically placed over the object in relation to the user input. An example of the use of the application. After the start, the blue exclamation marks are placed over the object that can be interacted. Tapping on the visualization over the sensor, a menu listing the functionality of the objects is shown. After selecting Add to Rule, the visualization changes and a particle effect is activated. Also, recommendations are placed over other related objects. Recommendations in this context can be presented in the form of complete rules or rule fragments to complete the automation that the user is currently defining. From previous experiences, we noticed that users tend to prefer the latter approach, hence we focused on this kind of recommendations. There are some peculiarities of recommendations in augmented reality setting. The first is that the creation of rules does not necessarily occur in a sequential manner. Then we have to consider that mobile phones have limited screen space. Hence, we have to maximize the utility of the presented suggestions, also considering their diversity, in addition to their relevance to the user input. Recommendations are generated by exploiting the dog-to-vec model. During the use, the rule fragment inserted by the user is passed to the preprocessor, which generates its natural language description. This description is passed to the dog-to-vec model, which checks the similarity of this sentence with the other descriptions stored into the dataset. The most relevant are passed to the post processor, which filters out rules that cannot be activated by user context, and separates the remaining into rule fragments. The fragments are passed to the quality score finalizer, which generates a final score also considering a diversity metric. We performed a user study to assess this solution. 15 participants were recruited. They had to perform some tasks in a real flat, equipped with 15 connected objects and 7 services, each of them exposing multiple functionalities. It was a within-subject study where each participant tested both with and without recommendation support conditions. Two smartphone scenarios were devised, and for each one, participants had to compose 4 automations, 2 simple and 2 compound. In half of the composition tasks, they had to check for recommendations and eventually select them. To better assess the recommendation system, they were free to select which object and services they prefer. The last task was to inspect the created automation using the Explore Environment functionality. Also, the timing for completing each task was recorded. After the tasks, participants had to fill in a questionnaire with statements in Likert scale and open questions. We will not go deeply into the responses, but we observed no differences into the perception of easiness to use and satisfaction between the application versions and between the simple and compound tasks. Also, we observed that the AR-related features, for instance the description of the created automation placed over the objects, were among the most appreciated. About recommendations, participants generally found them useful and select them 71% of times in the related tasks. But the use of recommendations do not speed up the composition process, and also participants found that they can be improved. In conclusion, we have presented the design and implementation of an approach to defining automation in smart environment using augmented reality. Future steps are to further exploit augmented reality for making more trigger action concepts perceivable, for instance, how to define services in augmented reality and how to make temporal aspects of rules more understandable. Second improvement is to improve the recommender system, for instance, considering both a large language model together with a collaborative filtering approach. And finally, we got to study how to further improve the transparency of a smart home system using augmented reality. So, how to help users with the debugging of conflicts between automations, for instance, showing the reason why or why not an automation has been activated, or what if something changed into the environment, and possible solution to the conflicts. This concludes my presentation. Thank you so much for your attention.